secondary overcurrent protection for a transformer needs to be located on the load side of the transformer as close as practicable to the transformer itself. In a situation where the secondary overcurrent protection is located approximately 120 feet away from the transformer, the protection should be placed at the point where the secondary conductors connect to the load. If the primary overcurrent protection is rated at 125% of the transformer's full load current, additional secondary overcurrent protection is not required, provided that the primary protection is located at the transformer. The secondary conductors are sized appropriately for the transformer's full load current, and the secondary conductors are protected against physical damage. Regarding fire rating requirements, a room housing a 150 kVA transformer with a maximum temperature rating of 155 degrees Celsius, which is class 155 insulation, must have a fire resistance rating of at least 1 hour. Therefore, the secondary overcurrent protection must be located at the load side of the transformer, approximately 120 feet away in the specified case. If the primary overcurrent protection is rated at 125% of the transformer's full load current, no additional secondary overcurrent protection is required as long as the previously mentioned conditions are met. And the room housing the transformer must be rated for 1 hour fire resistance due to the transformer's class 155 insulation. Transformers are critical components in electrical power distribution systems responsible for stepping up or stepping down voltage levels to match the requirements of different equipment and loads. Proper overcurrent protection is essential to safeguard transformers from damage caused by excessive current flow, which can result from faults, overloads, or short circuits. Overcurrent protection devices, such as fuses and circuit breakers, are designed to interrupt the flow of current when it exceeds a predetermined threshold, thereby preventing overheating, insulation breakdown, and potential fire hazards. The location of overcurrent protection devices is a crucial aspect of transformer protection, as it directly affects the effectiveness of the protection scheme. In general, overcurrent protection should be placed as close as possible to the source of potential faults, such as the transformer windings or the connected load. This minimizes the amount of unprotected conductor length and reduces the likelihood of damage to equipment or conductors in the event of a fault. On the primary side of a transformer, overcurrent protection is typically provided by a circuit breaker or fuses located at the incoming power source. This protection is intended to protect the transformer from faults originating within the transformer itself or on the primary side of the distribution system. The size and type of overcurrent protection device must be carefully selected to coordinate with the transformer's impedance and thermal characteristics, as well as the characteristics of the upstream power system. On the secondary side of a transformer, overcurrent protection is necessary to protect the transformer and the downstream loads from faults or overloads. The location of the secondary overcurrent protection depends on the specific application and the configuration of the electrical system. In some cases, a secondary overcurrent protection may be located directly at the transformer, while in other cases it may be located at a remote distribution panel or load center. According to electrical codes and standards, such as the National Electrical Code, the secondary overcurrent protection must be located at the point where the secondary conductors receive their supply, which is typically at the load side of the transformer. This ensures that the entire length of the secondary conductors is protected against overcurrent conditions. The distance between the transformer and the secondary overcurrent protection should be as short as practicable to minimize the risk of damage to the conductors. In situations where the secondary overcurrent protection is located a significant distance away from the transformer, such as 120 feet, it is essential to ensure that the conductors are properly sized and protected against physical damage. The conductors must be able to carry the full load current of the transformer without overheating, and they must be protected from mechanical stress, abrasion, and other potential hazards. If the primary overcurrent protection is sized appropriately and located at the transformer, it may be possible to eliminate the need for additional secondary overcurrent protection. However, this is only permissible if the primary protection provides adequate protection for the secondary conductors and the connected loads. Electrical codes typically allow the primary overcurrent protection to serve as the sole means of protection for the secondary conductors if the primary protection is rated at no more than 125% of the transformer's full load current. In this case, the secondary conductors must be sized to carry at least the full load current of the transformer, and they must be protected against physical damage. Furthermore, the primary overcurrent protection must be located at the transformer to ensure that it provides adequate protection for the transformer itself. In addition to overcurrent protection, fire safety is another important consideration in transformer installations. Transformers can pose a fire hazard due to the presence of flammable materials such as oil or insulation and the potential for overheating or arcing. To mitigate this risk, electrical codes often require transformers to be installed in fire-resistant enclosures or rooms. The fire resistance rating of the enclosure or room depends on the size and type of the transformer, as well as the occupancy of the surrounding area. For example, a 150 kVA transformer with class 155 insulation, which has a maximum temperature rating of 155 degrees Celsius, may be required to be installed in a room with a fire resistance rating of at least 1 IR. This means that the walls, floor, and ceiling of the room must be able to withstand exposure to fire for at least 1 IO without collapsing or allowing the fire to spread to adjacent areas. The fire resistance rating is typically determined by a standard fire test, such as the one conducted by Underwriters Laboratories, also known as UL. In addition to fire resistance, transformer rooms should also be equipped with fire detection and suppression systems such as smoke detectors and fire sprinklers. These systems can help to detect and extinguish fires quickly, minimizing the damage and risk to occupants. Proper ventilation is also important to prevent overheating and the buildup of flammable gases. The ventilation system should be designed to provide adequate airflow to the transformer while preventing the entry of dust, moisture, and other contaminants. Regular inspection and maintenance of transformers and their associated protection systems are essential to ensure their safe and reliable operation. Inspection should include checking for signs of damage, overheating, or leakage, as well as testing the functionality of overcurrent protection devices and fire suppression systems. Maintenance should include cleaning, lubrication, and replacement of worn or damaged components. By following these guidelines and adhering to applicable electrical codes and standards, it is possible to ensure the safe and reliable operation of transformers in a variety of applications. These are a few examples related to transformers. Firstly, sizing the transformer involves determining the appropriate kVA rating for a given application, which requires considering the connected load, the diversity factor, and the anticipated future growth. Secondly, calculating the transformer's full load current involves dividing the kVA rating by the voltage and multiplying by a factor to account for three-phase systems. Thirdly, selecting overcurrent protection devices involves choosing fuses or circuit breakers with appropriate current and interrupting ratings to protect the transformer from overloads and short circuits. Fourthly, coordinating overcurrent protection involves ensuring that the overcurrent protection devices are coordinated to minimize nuisance tripping and to provide selective tripping in the event of a fault. Fifthly, grounding the transformer involves connecting the transformer's neutral point to ground to provide a low impedance path for fault currents and to prevent voltage transients. Sixthly, testing the transformer involves performing various tests such as insulation resistance tests, turns ratio tests, and polarity tests to verify the transformer's condition and performance. Seventhly, maintaining the transformer involves performing regular inspections, cleaning, and lubrication to prevent failures and to extend the transformer's lifespan. Eighthly, troubleshooting transformer problems involves using various diagnostic techniques such as voltage and current measurements, insulation resistance tests, and visual inspections to identify the cause of transformer failures. Ninthly, understanding transformer nameplate data involves interpreting the information provided in the transformer's nameplate, such as the kVA rating, voltage ratings, impedance, and insulation class. And 10thly, complying with transformer regulations involves adhering to applicable electrical codes and standards such as the National Electrical Code and local regulations regarding transformer installations and maintenance. Furthermore, transformers are static electrical devices that transfer energy from one circuit to another through electromagnetic induction. They are essential components in electrical power systems, enabling the efficient transmission and distribution of electricity over long distances. Transformers consist of two or more coils of wire, called windings, that are electrically isolated but magnetically linked. The primary winding is connected to the source of electrical energy, while the secondary winding is connected to the load. When an alternating current flows through the primary winding, it creates a magnetic field that induces a voltage in the secondary winding. The ratio of the number of turns in the primary winding to the number of turns in the secondary winding determines the voltage transformation ratio. Transformers can be classified into several types based on their construction, application, and voltage transformation ratio. Power transformers are used in high-voltage transmission and distribution systems to step up or step down voltage levels. Distribution transformers are used to supply power to residential, commercial, and industrial customers. Instrument transformers are used to measure voltage and current in high-voltage circuits. Autotransformers have a single winding that serves as both a primary and secondary winding. Step-up transformers increase the voltage from the primary to the secondary winding, while step-down transformers decrease the voltage. Isolation transformers provide electrical isolation between the primary and secondary circuits. Transformers are designed to operate at specific voltage and frequency ratings. The voltage rating indicates the maximum voltage that can be applied to the primary and secondary windings without causing damage. The frequency rating indicates the frequency of the alternating current that the transformer is designed to operate with. Transformers are also characterized by their kVA rating, which indicates the apparent power that the transformer can deliver without exceeding its temperature limits. The impedance of a transformer is a measure of its opposition to the flow of alternating current. It is an important parameter for determining the transformer's short-circuit current and for coordinating overcurrent protection devices. The efficiency of a transformer is the ratio of the output power to the input power. Transformers are typically very efficient, with efficiencies ranging from 95% to 99%. The losses in a transformer are due to hysteresis, eddy currents, and copper losses. Hysteresis losses are caused by the energy required to magnetize and demagnetize the core material. Eddy current losses are caused by circulating currents induced in the core material by the changing magnetic field. Copper losses are caused by the resistance of the windings. Transformers are typically cooled by oil, air, or forced air. Oil-cooled transformers are immersed in oil, which acts as an insulator and a coolant. Air-cooled transformers rely on natural convection to dissipate heat. Forced air-cooled transformers use fans to circulate air over the transformer windings. Transformers require regular maintenance to ensure their safe and reliable operation. Maintenance activities include inspecting the transformer for signs of damage, cleaning the transformer windings and core, testing the insulation resistance, and checking the oil level and condition. Transformers are protected from overcurrents by fuses or circuit breakers. The overcurrent protection devices should be sized to protect the transformer from overloads and short circuits. Transformers are also protected from voltage surges by surge arresters. Surge arresters are devices that divert high voltage surges to ground, preventing them from damaging the transformer insulation. Transformers are essential components in modern electrical power systems. They enable the efficient transmission and distribution of electricity over long distances, and they are used in a wide variety of applications. Understanding the principles of operation, construction, and maintenance of transformers is essential for electrical engineers and technicians. Transformers play a crucial role in the efficient and reliable distribution of electrical power. These devices are designed to step up or step down voltage levels, allowing electricity to be transmitted over long distances with minimal losses and then distributed to homes and businesses at safe and usable voltages. The operation of a transformer is based on the principle of electromagnetic induction. A transformer consists of two or more coils of wire, called windings, that are electrically isolated but magnetically linked. The primary winding is connected to the source of alternating current, while the secondary winding is connected to the load. When alternating current flows through the primary winding, it creates a changing magnetic field. This changing magnetic field induces a voltage in the secondary winding. The magnitude of the induced voltage is proportional to the ratio of the number of turns in the primary and secondary windings. This ratio is known as the turns ratio. If the turns ratio is greater than 1, the transformer is a step-down transformer and the voltage is reduced from the primary to the secondary. If the turns ratio is less than 1, the transformer is a step-up transformer and the voltage is increased from the primary to the secondary. Transformers are designed to operate at specific voltage and frequency ratings. The voltage rating indicates the maximum voltage that can be applied to the primary and secondary windings without causing damage. The frequency rating indicates the frequency of the alternating current that the transformer is designed to operate with, typically 50 Hz or 60 Hz. Transformers are also characterized by their kVA rating, which indicates the apparent power that the transformer can deliver without exceeding its temperature limits. The kVA rating is determined by the transformer's design and the materials used in its construction. Transformers are typically very efficient, with efficiencies ranging from 95% to 99%. The losses in a transformer are due to hysteresis, eddy currents, and copper losses. Hysteresis losses are caused by the energy required to magnetize and demagnetize the core material. Eddy current losses are caused by circulating currents induced in the core material by the changing magnetic field. Copper losses are caused by the resistance of the windings. These losses generate heat, which must be dissipated to prevent the transformer from overheating. Transformers are typically cooled by oil, air, or forced air. Oil-cooled transformers are immersed in oil, which acts as an insulator and a coolant. The oil circulates through the transformer, carrying heat away from the windings and core. Air-cooled transformers rely on natural convection to dissipate heat. The transformer windings and core are exposed to the air, allowing heat to be radiated away. Forced air-cooled transformers use fans to circulate air over the transformer windings and core, increasing the rate of heat dissipation. Transformers require regular maintenance to ensure their safe and reliable operation. Maintenance activities include inspecting the transformer for signs of damage, cleaning the transformer windings and core, testing the insulation resistance, and checking the oil level and condition. The insulation resistance test measures the resistance of the insulation between the windings and the core. A low insulation resistance indicates that the insulation is deteriorating and needs to be replaced. The oil level and condition should be checked regularly to ensure that the oil is clean and free of contaminants. Transformers are protected from overcurrents by fuses or circuit breakers. The overcurrent protection devices should be sized to protect the transformer from overloads and short circuits. Overloads occur when the transformer is supplying more power than it is designed to handle. Short circuits occur when there is a low resistance path between 2 points in the circuit. Both overloads and short circuits can cause the transformer to overheat and fail. Transformers are also protected from voltage surges by surge arresters. Surge arresters are devices that divert high voltage surges to ground, preventing them from damaging the transformer insulation. Voltage surges can be caused by lightning strikes, switching operations, or other events. Surge arresters are typically installed on the primary side of the transformer to protect it from incoming surges. Transformers are essential components in modern electrical power systems. They enable the efficient transmission and distribution of electricity over long distances, and they are used in a wide variety of applications. Understanding the principles of operation, construction, and maintenance of transformers is essential for electrical engineers and technicians.